Thank you so much. Yeah, thank you. Okay, so I'm very happy to speak to you. I have, as usual, way too many slides and 30 minutes, so I have a lot I would love to tell you about, and I will have things thrown at me if I take too long to tell you about them. So I'm not bearing any leads here. Of my belief is that as a field, we have always been held back really by a lack of data, difficulty accessing data, and a lot of, I would say, overemphasis on risks of using data and underemphasis on benefits of using data, particularly when it comes to clinical text. So, I thought I'd start by highlighting just the tremendous progress that we've all seen over the past few years. This is 2 years old, so it might as well be ancient history at this point. Just in terms of large language models coming out and really being impressive for their coherence. I was very acerbic of large language models for a long time, but it's pretty hard to deny their utility. Obviously, they have their issues, but they are certainly useful in a lot of tasks, and they're only getting better. So this is honestly a really exciting time. It's a little bit scary for some people who say it's difficult to do research now because of all these large language models, but I think the opposite. I think there's so much fiddly stuff in NLP that you can gloss over with a really nice model nowadays. And this extends into medicine, so there's quite a few different evaluations of medical tasks for these large language models, and this is from Google's recent work on MedGemini, where they were evaluating how well this large language model answered USMLE questions, which are essentially questions asked to doctors in order to make sure that they're good at their doctoring stuff. And it does fairly well, though of course there are some limitations to these benchmarks, and they are multiple choice, so that's always a little bit easier. I'm sure doctors wish patients came in with a multiple choice list of, hey, which one of these is my diagnosis? It would make their life a lot easier. So there's obviously limitations, but still quite impressive performance. And really moving into the multimodal domain, again, also MedGemini, which can read MRIs, and that response at the bottom is actually its written response to this series of images, which is just really incredible. I wouldn't have been able to say that we could do this 4 or 5 years ago. Just really incredible. The other interesting thing, this is the example that Google picked to put on their blog post to advertise to everyone. And they note this themselves, that it actually noted old left basilar ganglia infarct, which was not mentioned by the radiologist who reviewed that. So that's very interesting. At the same time, basilar ganglia is not a thing because it's a mistranscription from the speech-to-text software that occurs so frequently in this data that the model actually thinks it's your basilar ganglia and not your basal ganglia. So that's kind of interesting to see that it's at the same time really impressive, picking up things that we might have missed, might augment things, and at the same time doing it in a really silly way that sort of undermines your trust in these models. So we look at this sort of progress in technology, and then we compare it to actual clinical practice. And I've worked a lot in critical care, and we still use SOFA in order to diagnose or grade sepsis in many ways. SOFA was originally published in 1996. The only thing that has really changed about SOFA in those 30 years is changed the first word to mean sequential rather than sepsis related. And just for reference, this was me in 1996. So a lot has changed. I don't know if I'm like doing a move there, or I had a bad back then and still have a bad back now. But either way, it's shocking to me that we haven't really made this advance in progress, and there's some reasons why, and my emphasis is that really it's in this lack of data, difficulty accessing data, and the fact that we don't use all this data collected during routine healthcare in order to improve practice. So there's a great example of the fact that this does work, and that's the ImageNet challenge, or the ILSSVRC challenge. ImageNet and the challenge are slightly different things, and I'm going to abuse terminology and just call it ImageNet because that acronym is horrendous. horrendous to pronounce. But essentially, this was a data set released over a decade ago, 200,000 photographs, and they labeled it with 1,000 object categories. 1,000 was a lot at the time. That's a lot of different categories. It's very hard to model. And basically, back in 2010, we had all these feature extraction models, and we had Gabor filters, and it was all very elaborate and reminds me a lot of all the weird stuff we do in NLP with, parsers and whatnot. And average accuracy was very, very poor. Some people are getting every single question wrong there, which is not a very good score. And as we move along, 2012, ImageNet, AlexNet, this sort of deep learning revolution starts to kick off. Obviously, they had some deep learning models before 2012, but the combination of those deep learning models and being able to run them on the GPU really enabled, large scale training, and that sort of kicked off higher performance. And by 2017, we have quote unquote superhuman performance on this data set. In reality, humans get really bored of labeling objects and images very quickly, so it's hard to say that what human performance really is in this. But at the very least, we got very good in only 5 to 7 years. And during that time, we also started using a lot more GPUs because that became the way to do this. So it's interesting to ask, how did they actually access the data? It's an entirely different world. They went to this website, they clicked download, and then they had the data. Okay, that was it. Oh my goodness, wonderful. And I remember talking to some of the researchers, and they're like, "Oh yeah, I just use these 2 data sets. It's great." I will say, since early 2021, they added a data use agreement. So now you have to click I agree, and then you can download. So this is a little bit more regulation there, but not much. If we compare that to how we do it in medicine, it's very different. You need REB, IRB, CAG, whatever the acronym is in your respective country is. And then you say, yes, I need all the data. And they're like, what do you mean you need all the data? You specify all the parts of the data that you need. You need departmental improvements. We need a data transfer agreement. We need to talk to legal. IT says you need to demonstrate security. So you're saying, oh, I've got this locked cabinet. That locked cabinet is in this locked room, in this locked building, in this locked country. It's kind of crazy. And then once you go through all those processes, now you need IT support to extract the data, and they say, oh, you need 100 records. If you've ever used Epic, they're saying, why can't you just use a Workbench report? I've actually talked with teams, and I said, yes, okay, I have all the approvals for this study. I need to pull 1,000 notes, and they said, whoa, 1,000 notes. I don't think our servers can handle that, which surprised me because surely they can. Surely Microsoft SQL Server handles more than 1,000 things at a time. It's pretty robust software. Then you get a data extract, it's all wrong. You go back and forth, and then you realize you forgot something, and you need to go through all the approval processes again. And you're like, okay, everything is fine. So this, obviously I'm being a bit flippant in some ways, but this really does happen all the time. And it really holds us back. I've had students who, great project, great student, and they spend their entire time doing nothing because it took us 9 months to get the data. And by the time they're ready, they're already graduated with a different project. So the thing that I want to emphasize is that you actually can share healthcare data. And I can say this confidently because we did it, and I can say it confidently with free text clinical notes because we did that. So I'm going to talk about Mimic. Mimic is my first baby. Don't tell my current children this, but Mimic, very dear to my heart. This picture is actually Mimic 1, which predates me quite significantly. It was a host of paper records, all collected mainly to support electrocardiogram analysis, but essentially, a lot of work. They manually transcribed these to a digital computer. I'm so thankful I didn't have to do any of that. That would have been very difficult. They shifted with Mimic 2 to digital, and then I came in at Mimic 3. And essentially what Mimic is we take critically ill patients. So these are patients in the ICU. And they are receiving life-saving treatment. We heard a lot about critically ill patients and ventilators during the pandemic. So many of us are fairly familiar with this sort of last line of defense of the hospital. And we take all that information, we transform it a little bit, and we make it available. And I'll talk a bit more about this process. What it actually looks like, I like to show people the data because it's really not that scary. Is a lot of it is this entity attribute value model where you say, okay, who are we measuring? And we have a random number which doesn't mean anything to represent an individual. We have what we're measuring, which is the heart rhythm or what have you, when we measured it, and what was the value. And that's it, except there's hundreds of millions of rows like this. And you can start to do these kind of nice plots. So this is just one patient for a little bit of time, and you can easily start to see different patterns emerging. You can see how rich this data is, how we can learn from it. You can see in the middle there that they switch from sinus rhythm to atrial fibrillation. That's those pink squares in the middle, and their heart rate goes up at the same time. And it's like, oh, kind of cool because this is what happens, and it's obvious, but I like seeing data. So that's sort of what Mimic is, and it's grown over the years. So it initially started just in critical care. We sort of started adding additional modules to it. So we added data from the emergency room. We added chest X-ray data. We added laboratory data. We improved our laboratory data. So you have quite a comprehensive view. This is an example of a patient. They sort of start ill. They go into the emergency room. You get some vital signs for them when they're in the emergency room. You might take their chest X-ray if there's a good reason for doing it. So you have the image, you have the radiology report there. You might take some microbiology, some laboratory measurements. Then they go to the ICU. You have all the charted data, and then they go home. And so this is an example this is the image that we published in the paper with Mimic CXR. This is the actual radiology report and the actual images. And so this is publicly accessible data. So that means that any one of you could apply for access and within a week have access to 200,000 radiology reports, which look like this, and around 300,000 images, which look like that, which is really, really powerful, really powerful, and really, really exciting, which is why I work on it. And so I included this for people's reference later so that they know where things are. Everything is hosted on PhysioNet, and there are these different modules. This is an image, it's slightly older, it's from a few years ago, but this is our sort of user base from a single month in 2021. And you can see that basically people around the world use Mimic. Ironically, there's no one here in Bolivia, even though one of the creators of Mimic is from Bolivia, so I like to tease him about that all the time. I'm like, go back to your country, spread the good word. But it's really impressive, and this is actually really stating how difficult to access medical data is really a global problem. It's not a local problem. Everybody is looking for a solution to this problem, because I think everybody would prefer to use local data if they could, but for various reasons it's too difficult. So what really enabled us to share the data? I really love de-identification. I honestly think it's an amazingly powerful technique. I think, yes, it's not perfect. Very few things in this world are. But I think it is very, very powerful. And I say this, having tried to break my own de-identification and realizing how hard it is. So what really enabled us, and how did we share this data set? Well, we took 3 steps. Step 1, we got ethics approval. Step 2, we created the data set. And step 3, we shared the data set. It was all that easy. Go forth and share your data sets. This figure is actually from the original IRB application, which I love it. It's so retro. But this was essentially our process. We collected data from the Beth Israel Deaconess Medical Center. Was so important that the leadership at that hospital were very forward thinking. They were totally on board. They saw the value of data sharing. They saw the value that could be created from this data set, and they pushed for it. They helped us. They were not adversarial, and that's super important. I think you never want to be pushing uphill. They should, your hospital partners should be on the same side. You can see there is a hints of a VPN and secure file transfer. There are also these encrypted removable disks. That's because we had a very, very sophisticated data transfer system of me carrying a hard drive on the train, which was encrypted. We've improved our technology, but that took some time. And we basically at MIT de-identified this data and made it available. So let's go through this in sort of a little bit more detail. So the first step, I could spend hours and hours telling you about how we created Mimic, and I'm very happy to talk about the data set. I actually think one of the interesting things about medicine is a lot of the data is the same. I've seen data in almost every single continent except Antarctica, obviously, if that's a continent. And you roughly get the same thing. You get labs, you get micro, you get charted data, you get these things. So we reorganized the data to be easier to use. This is actually trickier than it looked because the data was undocumented, obviously. And then it's hard to simplify the data and not apply assumptions that might negatively impact downstream research. So that balance is actually very tricky to do. Okay, so the next step was de-identification, and I'll spend a bit more time on this because this was really important. And we were really enabled by HIPAA, by this legislation in the US, which came about because of some concerns around identifiability of data. And what HIPAA did, which I think is great, is it had this safe harbor provision which said, hey, if you remove these 18 identifiers, then the data is de-identified and you can use it for research. And what was really powerful about this was it was a prescriptive definition of de-identification. Canada does not do this. As far as I know, the UK does not do this. And the advantage of a prescriptive definition is you can actually say, look, we did this, we'll move forward. And you don't get stuck in this debate around whether it's really de-identified. So the identifiers are very sensible. There's names, dates, that sort of thing. There's category 18, which is like and everything else. So there's kind of this catch-all category, which is very ambiguous, but that didn't really stop the utility of this. And actually a lot of other countries, including us in Canada, we often de-identify to the HIPAA standard because it's a prescriptive definition that exists that we can hit. And there are some interesting provisions. So they require you to remove ages which are over 89 because they realize that, oh, there could be these risky subgroups that you want to remove additional information, which was a great idea, though I'm not sure over 89 is that much of a risky subgroup anymore. So de-identification of structured clinical data, what a dream, Name column, delete name from table patient, done, de-identified. Free text clinical, though, it's a little bit more challenging in a lot of ways, and this is really where we put most of our efforts. And I can, if I have more time, I would talk more about it, but we had various approaches, and I'll sort of tell the story of how we actually de-identified Mimic CXR radiology reports. So this is actually how we de-identified those reports and released them. I really like radiology reports because they're really easy to de-identify. Radiologists, they don't really talk about the patient, they talk about the image. It's very convenient. And so you have very low risk, very low frequency of PHI in the notes to begin with. So this was a model, that we trained back in 2020. If anybody has ever seen Portlandia, there's like a joke where, you put a bird on it in order to make something popular in a store. And back in 2020, everyone was putting a BERT on it and like training these BERT models to do everything, A, B, C, D, E, F, G. So we trained a BERT model to do de-identification. It's very good. That's basically what this table sort of tells you. It was, not earth-shatteringly better than the rest, 1% F1, but very good considering we just took BERT, trained it on a data set, and evaluated it, and we didn't really do a lot of exploration around there. And we did try some other techniques, and they did okay. So then we tried this on the actual radiology reports, and this is sort of a fake radiology report. And we found that it didn't do great. Actually, it missed 8% of the PHI tokens in our annotated data set, initial one of 1,000 reports. It would miss these very obvious examples like these dates, radiology reports. They have structured reporting at the hospital where we source this data from, so it's very convenient. And it would miss really, really obvious things that that you could pick up with a pattern. It would actually be inconsistently annotating some things like these dates, which was also fairly annoying. So we did what any good NLP researcher does, and we turned to regular expressions, lots of regular expressions, and anyone who says rule-based approaches are much simpler than neural networks has never actually tried to implement a large number of rule-based approaches. These are a nightmare, absolutely a nightmare. But they are incredibly effective when you customize them to your data set. So we annotated more notes, ended up with 99.92% sensitivity, which was excellent. Technically, we perfectly de-identified the notes according to HIPAA, because HIPAA does not actually consider providers to be real people. No, it actually doesn't consider provider names or provider information to be protected health information, because it doesn't correspond to the patient. However, we do, because we like the doctors we work with, so we try to help them out. And so, you know, we missed a few names which were hard to pick up, honestly. They were like, someone's name was like Rose or something like that. You know, a common word that was also a name is the flavor of it. So still, it was pretty good. And we published it and we said, look, if you do the math on 0.08% error here times, you know, 300,000 or 200,000 reports, then the math works out that there's probably PHI in the data set. And that was acceptable to us. And so why was that? It's because we had this dissemination process that we feel adequately safeguards the data from imperfect de-identification. So how is Mimic actually disseminated? And you could follow this process. So you could also consider this as a tutorial if you want access to millions of clinical notes by next week. Then you can start writing notes. Basically, you manually verify that this person's a legitimate user. So this is actually a manual process. It's still a manual process. We have tens of thousands of users approved every year. So it's a very tiring manual process, but it works. I think there are better approaches to doing this in terms of using single sign-on and federated identity and so on and so forth. But this system has been in place for a while. So this is what happens first: is you register and then you get credentialed by applying and saying you're a real person and I would like to do research with the data for this purpose, and somebody actually checks to make sure you're real and you have a good use of the data, good reason to use the data. Then you do human subjects training or human participants training. I think it is called human subjects training in the US, which basically teaches you all the things you should know about doing research with humans as participants. The nice thing about this training course is you can actually click a link. You could click that link and see my score on this quiz, and I got one conflict of interest 4 out of 5, so you can make fun of me about that later. And then you sign a data use agreement, and this is the entire data use agreement. This is not a 9-page lawyered up data use agreement. It's very simple. Don't be a bad guy. If you find PHI, email us about it. Don't share the data. And it's all very innocuous, human readable, and everybody sort of adheres to this to the best of their ability. There is one provision which we added, which was essentially share your code, because we feel very strongly about this. And academics had no problems with this, and I get a lot of emails from people in industry yelling at me about how they have to share code. But, you know, I think it's important. Okay, so why did we release data using this mechanism? It's because you can do very interesting things. So some of our work was really showing that, and you can read more about it here, that if you take clinical notes and you train a model from scratch, then you actually do really, really well. So this is even better than general domain models up to a point. And you get trade-offs in terms of how much compute and how much data, but our specialized sort of clinical models, which were trained using clinical notes, were basically matching models with 10 times more compute, which were trained on general domain. So it's very useful to be able to have a large clinical corpus and train a model. We are getting benefits, and we see that in our evaluation. So for example, in this one, our clinical model here was doing a lot better than the sort of general T5 model. doing much better than prompting. So the dashed lines are sort of prompting, and as you're getting more questions and fine-tuning this model, you're getting a lot better performance. So I would love to talk more about this, but I always put too many slides in things. I think one of the most interesting things is actually learning stuff that you didn't know was there. So this was a very interesting paper where they were able to classify sex from retinal fundus imaging, which I've talked to a few ophthalmologists, and they all looked at me and they're like, "No, you can't." I was like, "I don't know. Looks like you can," and I guess it is possible, but it's interesting that it's sort of there's information there that is predictive of this that we don't know, and I think that's one of the most interesting parts of machine learning. It's only possible if people can access the raw data. And sort of last point here is that sort of free text really enables a lot of research that can't be done with structured data, because the default interface to the electronic health record for clinical providers is really free text. Because as much as you would like to build a structured EHR that you can capture everything in, eventually you'll miss something, and eventually they'll write it in free text. And so there's so many studies which are just enabled because when people are working on a study and they say, "Oh, I want to do this, I want to do this," and I say, "Okay, oh, you need the labs, they're here, this is here, this is here, oh, you need this." Okay, that will probably be in the discharge summary, and their project is not blocked because they can actually access the data. So this is an example of one where all the information they needed was available in the structured data, except whether someone was on an SSRI before admission. That was only in the discharge summary. And because we published these free text notes, they were able to extract this. Took some effort, of course, able to do this study. And this was sort of the first time anyone had demonstrated that SSRIs actually have an association with increased risk of in-hospital mortality, which is interesting. So Mimic has actually ended up being used quite a few. There was a systematic review of clinical text data sets released a month ago, which is interesting. I recommend reading it. And this was the list of sort of data sets that papers used in their study. And if you actually look and break this down, so there's a whole bunch of different data sets, a lot of different challenge data sets, and 2C2 popping up a lot. There's actually really two sources of data. One is Mimic and BIDMC. The other one is Partners Healthcare through these I2B2 challenges. And then really not that much else. There's really not that much clinical data. And I think it's kind of really unfortunate that most of the NLP work and most of these NLP benchmarks are run on essentially data from two hospitals, or Partners is a hospital system, but I think you get the idea. And this is going to hold us back as a field, because if we look at the performance of models, really more data is increasing our performance across the board. And this was OpenAI's bet that was proven true, that you just add more data, you add more compute, you take the same approach more or less, and you get a better model that starts to have this quite incredible behavior. And we are quite far off the sort of trillions of tokens that these models are working on. I think there's a really great, very short essay from Rich Sutton about the bitter lesson of, you're doing NLP research or AI research, and you're really excited, you have this new methodology, and then somebody comes along and basically just does search 10 times faster or uses 10 times more data, and they crush your method. And you're really bitter about it, but it's actually the way it goes, because search and learning are very powerful techniques, and if you can enable those techniques, then they really scale. So this talk is a little bit preachy. I'm sorry about it. I'm trying to convert everyone to my story. I do think there are some alternatives. Happily, I don't have to talk about TREs. We just heard about them. That's very convenient. Thank you. There's this approach of, let's process the data a little bit, and let's structure the data and only release that structured data, and we'll reduce risk and mitigate risk that way. Great idea. Really hard to do. So there's a very famous example of chest X-ray 14. So was this chest X-ray data set where basically they took images and then they took the radiology reports, but they didn't release the free text radiology reports. They released structured data. So they released these zeros and ones over here on the right, and they didn't release the actual raw radiology report on the left. And basically what ended up happening is a radiologist went through all the images and said, actually, 40% of these labels are wrong, 20 to 40%, depending on the category. And that's because NLP is hard. So introducing, an AI hard problem in the middle of your data release strategy is, going to cause some issues. So it can work sometimes, but it's certainly not ideal for that point. There's a very prominent example oh, well, what if we give people synthetic data and we have private compute? I don't know what to call these safe havens. Open Safely is, I think, the biggest example of this. I think this is a wonderful initiative, but truly, I feel like it actually doesn't mesh with the way that data science is actually done, in my opinion. So I think it's very difficult to do data science with a synthetic data set and have results spit out to you. And the reason is from just my experience of working with Mimic and working with the data. So let's take a simple statement like excluded patients who are DNR/CMO. So DNR/CMO are code statuses. They don't want to receive treatment if they have an arrest. You can define this in Mimic in multiple ways. You can define it using the billing code on hospital discharge. You can define it using charted data from a nurse. You can define it using free text notes written by providers. All three of these give you a different definition, and it depends on your study which one you want to use, right? And data science is really this dialogue with the data, right? And if you can't actually see the data, if you can't actually investigate errors, if you can't actually understand why a model is behaving the way it was, then how are you expected to make any conclusions from that data which can then be used to change clinical practice? I mean, I don't think so. And it's not just in medicine. If you remember ImageNet, where I was talking about, oh, this great performance increase, a lot of people say, oh, this was neural networks did this. And a lot of people forget that every single year they had a conference talking about this challenge. And what they did in this conference every year was they talked about the data. So this is an example of a confusing label that happened. And so they were talking about, okay, well, some of the labels of this data are incorrect, right? This was an example of where my model is predicting that there's a dock, that there's a boat, but actually the ground truth is a paper towel because there's this tiny paper towel in the front, right? Another error that you can only realize is an error because you're looking at the data. And then, my favorite is that people were saying that this was ground truth is a sleeping bag, and this is just the label is incorrect. And I don't think that's a Hello Kitty in a sleeping bag. I think that's a pencil case. Similar now, that held true with ImageNet, 10 years ago. It's still true now. MedGemini, actually, its performance is contingent on this note at the top left that I hid before, where they actually had clinicians review the USMLE questions. And 7.5% of the questions, the clinician said, actually, this question is bad. Either the answer is wrong or it's ambiguous, some question where it's like, what infection does the patient have, A, B, C, or D? And it could be either A or B. And so the model was saying A and being penalized incorrectly. So they actually removed 7.5% of the questions, again, by looking at the data. And you can't do this kind of quality improvement if you don't have access to the data and don't see it. So, what about federated learning? I'm not going to. This is crazy. I mean, I struggle to get people to work with, spreadsheets, but we're going to have this federated learning system where we're like transferring weights across hospitals. Like, it's just crazy. I think federated learning is way too difficult to do. It's also a very, very niche use case. You can't do data science with federated learning. You can basically, at the moment, only train image classification models, which if you're doing it, great. And if you're doing anything else, it doesn't work for you. Okay, but sharing data is hard. Yes, it's very hard, and managing access is a lot of work. I can speak to this. I could speak to this. I'll do a little bit of a plug that doesn't have to be all bad. In that we actually, at Toronto, when working with the University of Toronto and TCARM, which is an AI center, we made an environment to support data sharing. This is funded by the Temerty family, philanthropic donation. They have money for decades, so it's not going anywhere, which is great. And it's essentially based off PhysioNet. We actually use the same code as PhysioNet, so we shared code and we gave back to PhysioNet because it's such a great resource, where you exactly what I talked about before. You sign in, you're registered as a real human, you take the necessary training and submit proof of it, you sign a data use agreement, you access the data. The only difference here is that we give you the data within Google Cloud Platform. You can't download it, you can't exfiltrate it easily. And that's, that I think that's all you need. Like, this is the modernization of Mimic in my view. I think it was great that we were able to share the data broadly, that people can access clinical data through Mimic. I think it's even safer now that you can create these environments relatively easily where people can quickly log in and access the data. So now you're like, okay, wait, but you just shared all your data. Now you're talking about a trusted research environment. And I think, yes, that's true, but this is an empathetic one, is my way of saying it. So I feel like a lot of trusted research environments kind of treat their users as hostile entities when they really shouldn't. So Health Data Nexus, downloading is disabled. Exfiltration is monitored, but you're sort of trusted to not be a bad actor. I'm sure there's obviously you have the data on your computer. You can take a mobile phone and scroll through all the data, and how am I going to stop that, right? So in theory, it's possible to remove data, but you're trusted not to do that. And I think that's a key step, is to trust the researchers. And there are other aspects of this as well, that you can install software, you're sort of trusted. And my view of this, having worked with the data a lot, is actually these environments should not be designed to prevent malfeasance. These environments should be designed to prevent accidents, because the reality is not that somebody comes into your environment and tries to steal the data so that they can do what? I mean, the threat model isn't even well articulated, honestly. They're like opportunistic attacks. I think they're so rare and so difficult that the probability of that is already very low. There's no insurance data, there's no social security numbers, so identity fraud is gone. So you start to reason about who is this bad actor, and there aren't that many threat models that really make sense. The real sort of issue is that people make mistakes. They accidentally upload data they shouldn't. They accidentally download data they shouldn't. They accidentally do blank. They didn't realize they needed to, have this cell count. It's just all, researchers who are learning best practices who make mistakes. And I think these environments should be designed with that user in mind, of how do we make sure this person is the best version of themselves, rather than assuming there's some bad actor that we have to stop. And so I'll sort of finish with this, because I think this is why I push so much for opening data as much as possible, for sharing data broadly, is because we are always talking about the risks of breaches, the risks of patient harm, the risks to patients about what if their data leak. But we never really talk about the risks of not sharing the data, right? We are sitting on terabytes of data that could be used in clinical practice to improve patient care, and we don't, because we're too afraid that somebody might re-identify Tony Blair or something like that, right? I find it a little bit frustrating, but also, really important to keep this in mind, that everything is a risk-benefit trade-off, and we always forget about that benefit when we're talking about patient data. So this is an actual example of someone who came into the emergency department. This is their electrocardiogram. I don't know if any of you are cardiologists. I'm not. There is an ST depression on sort of V4, right? I can do that much. My old boss was a cardiologist. He would yell at me if I didn't see that. But other than that, I don't know. The physician documented this as normal sinus rhythm. Okay, but it was not. There's actually, there is an occluded myocardial infarction here. Very difficult to pick up. Not picked up by the emergency room doctor. This woman was sent home. Next day, collapsed in her house, resuscitated, but eventually died. So this woman literally died, even though there were algorithms that existed that could say, hey, there's an occluded myocardial infarction, right? And we can say this with ECGs because we share ECGs, right? ECGs are not really considered personal identifiable information. So there's tons of ECG data. So there's been tons of development there. So there are now lots of algorithms to do these classification, and they can augment our care. So, there are these people who are actively being harmed by us not leveraging technology and not leveraging data that exists. And we need to remember that's happening, that, especially as our resources, our human resources start to get constrained, as we start to need to care for more people, technology is the highest leverage thing that we have in order to care for more people, right? And we should start taking advantage of that. And the first step of doing that is really unlocking the data for use by researchers like yourselves, right? Which is why I work so hard on sharing Mimic. So I'll end with this, which is basically, if you remember nothing else from what I said, right? So Mimic has been shared. Mimic contains data from over 70,000 patients, billions of data points, millions of de-identified free text clinical notes. That's not an exaggeration. There are 2 million radiology reports. It's been shared like this for 10 years to tens of thousands of users. They downloaded it to their laptops, which, I'm like the boogeyman to this conference and to the TREs, like I'm the evil person sharing data. And there's zero evidence of harm to any patient at BIDMC. Zero. I don't know of any. I would know of any, as far as I know. So like that is pretty powerful. Even if you use like a Laplacian sort of smoothing on this, it's 1 over a really big number risk of harm to patients. And I also know that of the startups of technology companies, medical technology companies in the US who are, developing algorithms for deployment in patient care, I want to say 80 to 90% of them use Mimic and use the data in Mimic to get themselves started. So it's really, really powerful for actually catalyzing improvements in care. So I'll end with that. I'll end with the statement that we can share medical data safely, and we should really try harder to do so.